Welcome! In this session, we'll explore an intriguing problem from LeetCode, titled Count of Smaller Numbers After Self. This problem challenges us to efficiently calculate how many smaller elements follow each number in an array. By the end, you'll understand the intuition and approaches to solving it. Let's dive in. The problem requires us to analyze an integer array nums of length n. For each element in the array, we need to determine how many smaller elements exist to its right. The result is returned as an array, where each position corresponds to the count of smaller numbers for the respective element in the input array. The constraints ensure that the input array can have up to 100,000 elements, and each value in the array will range between -10,000 and 10,000. Let's look at an example to understand the problem more clearly. Suppose nums is 5, 2, 6, 1. For the first element, 5, there are two smaller elements to its right, specifically 2 and 1. For the second element, 2, there is one smaller element to its right, which is 1. Similarly, for 6, there is also one smaller element to its right, and for 1, there are none. Thus, the output in this case is 2, 1, 1, 0. Now, to further elaborate, consider the provided example where nums is 5, 2, 6, 1. For nums 0, which is 5, two smaller numbers exist to its right, 2 and 1. For nums 1, the value is 2, and the only smaller element to its right is 1. When we look at nums 2, which is 6, there is again one smaller element to its right, which is 1. Finally, for nums 3, which is 1, there are no smaller elements to its right. Hence, the output becomes 2, 1, 1, 0. Another example is when nums is -1, -1. Here, since all elements are identical, no smaller numbers exist to the right of any element, resulting in an output of 0, 0. Similarly, if we have an array like 10, 9, 8, 7, where every element is strictly larger than the ones following it, the output will reflect the count of all subsequent elements for each position. For instance, the first element, 10, has three smaller numbers to its right, and so forth. In the example of nums equals 10, 9, 8, 7, the output is 3, 2, 1, 0. For nums 0 equals 10, there are three smaller elements to the right, 9, 8, and 7. For nums 1 equals 9, there are two smaller elements to the right, 8 and 7. Similarly, for nums 2 equals 8, there is one smaller element to the right, 7. Lastly, for nums 3 equals 7, there are no smaller elements to its right, resulting in 0. Now, considering the constraints, the input size can go up to 100,000 elements, and values range between -10,000 and 10,000. This means that brute force, or O, in superscript 2, approaches would be inefficient for larger inputs. A key requirement is to solve this problem in an optimized way, ideally within O, n log n, time complexity. Additionally, edge cases like arrays with a single element or arrays where all elements are identical must also be handled carefully. Finally, let's consider some edge cases to deepen our understanding. For a single element array like nums equals 1, the output is 0, because there are no elements to the right of the single value. If all elements in the array are identical, such as nums equals 5, 5, 5, 5, the output will be 0, 0, 0, 0, since no element is smaller than any other. For a strictly decreasing array like nums equals 4, 3, 2, 1, every element has all subsequent elements smaller than itself, resulting in 3, 2, 1, 0. Conversely, in a strictly increasing array like nums equals 1, 2, 3, 4, no element has a smaller number to its right, so the output is 0, 0, 0, 0. Understanding these edge cases is crucial for developing a robust solution that handles all possible scenarios effectively. To begin, one of the simplest ways to solve the problem is the brute force approach. The idea here is straightforward. For every element in the array, we check all the elements to its right and count how many are smaller. This is done using two nested loops, an outer loop that iterates through each element and an inner loop that compares that element to the ones following it. While this method is intuitive and doesn't require any additional data structures, its major drawback is efficiency. Since we scan the remaining array for each element, the time complexity is O, n squared, which becomes impractical for larger inputs, such as arrays with up to 10,000 elements. This inefficiency is why the brute force approach is not suitable for this problem. Another approach is to use a binary search tree, or BST, to dynamically maintain the numbers we've processed so far as we traverse the array from right to left. This structure allows us to efficiently count how many elements are smaller than the current number by leveraging the properties of the BST. As we iterate through the array, we insert each number into the tree and use it to calculate the count of smaller elements. While this approach has the potential to be faster than brute force, with a time complexity of O(n log n) for balanced BSTs, it faces challenges. In the worst case, the tree can become unbalanced, leading to a time complexity of O(n squared). Additionally, implementing a self-balancing BST, such as an AVL or red-black tree, adds complexity to the solution. These drawbacks make the BST approach less appealing for this problem. The Fenwick tree, also known as a binary index tree, provides another efficient solution. This approach involves mapping the numbers in the array to their ranks, which compresses the values into a manageable range suitable for the Fenwick tree. By iterating from right to left and querying the tree, we can quickly count how many smaller numbers have been encountered. After querying, we update the tree to include the current number. The pre-processing step of rank compression, combined with the tree operations, gives this method a time complexity of O(n log n), making it efficient. However, while the Fenwick tree is a powerful tool, it is slightly less intuitive and requires additional pre-processing compared to the chosen method. This makes it less desirable for this specific problem, despite its efficiency. The merge sort approach leverages the divide and conquer strategy to count smaller numbers during the merge step. As the array is divided into smaller subarrays and then merged, we can calculate, for each element in the left subarray, how many elements in the right subarray are smaller. By pairing each number with its original index, we ensure that the results are aligned with the input order. During the merge step, we compare elements from the two subarrays and update the count for the elements in the left subarray whenever we detect smaller elements from the right. This method is both efficient, with a time complexity of O(n log n), and relatively simple to implement, as it builds on the familiar framework of merge sort. Its combination of efficiency and simplicity makes it the preferred choice among the approaches considered. The key insight behind choosing the merge sort approach lies in the merging process itself. The way elements from the two subarrays are compared inherently provides the information needed to count smaller numbers. By processing subarrays recursively, we avoid redundant comparisons and maintain efficiency. Pairing each element with its index ensures that we can directly update the result array, preserving the original order. Compared to brute force, this approach is exponentially faster, and unlike the BST, it avoids the risk of inefficiencies due to tree imbalance. While the Fenwick tree is equally efficient, the merge sort approach is simpler to understand and implement, particularly for a static input like this. The trade-off is the use of auxiliary space, which is comparable to the Fenwick tree. However, for this problem, the ease of implementation and clarity provided by merge sort outweigh these concerns. In conclusion, the merge sort approach was selected because it offers the best balance between efficiency, simplicity, and ease of implementation. Its time complexity of O(n log n) makes it feasible for large inputs, and its straightforward logic ensures that it is accessible and practical to code. By leveraging the divide and conquer strategy, we can systematically count smaller numbers without redundant calculations, making it the most suitable solution for this problem. To solve this problem, we are given an array of integers, and for each element, we need to count how many elements to its right are smaller than it. For example, with the input array 5, 2, 6, 1, the expected output is 2, 1, 1, 0, because for each number, we count the smaller numbers that appear after it. The brute force approach starts by initializing an empty result array of the same size as the input and setting all its values to 0. This array will eventually hold the counts for each position. We then iterate over the input array using an outer loop, where the current index I represents the element we are analyzing. For each I, we use an inner loop to scan all elements to the right of nums I. By comparing each of these elements with nums I, we can count how many of them are smaller. This count is stored for the current index in the result array. This method, while straightforward, involves two loops, one nested inside the other, to compare all relevant pairs of elements. Once the inner loop finishes counting the smaller elements for the current number, we store the count in the corresponding index of the result array. After the outer loop completes its iteration over all elements, the result array is returned. Let's walk through an example to clarify. With the input nums equals 5, 2, 6, 1, we start with the first element, 5. We compare it with the elements to its right, 2, 6, 1. Out of these, only 2 and 1 are smaller than 5, so the count for the first position is 2. Next, we analyze 2, comparing it with the elements 6, 1. Here, only 1 is smaller, so the count for the second position is 1. For 6, we check the single remaining element, 1, which is smaller, resulting in a count of 1. Finally, for 1, there are no elements to its right, so the count is 0. The final result array becomes 2, 1, 1, 0, which matches the expected output. The brute force approach we just described uses nested loops, where the outer loop processes each element in the array, and the inner loop compares it with all elements to its right. This ensures that every relevant pair of elements is considered, but the downside is the high computational cost. Specifically, the time complexity of this approach is n squared, since the inner loop runs up to n times for each of the n elements. On the other hand, the space complexity is 1, because we only use the result array, which is proportional in size to the input array. While this approach is simple to understand and implement, it does not scale well for larger input sizes. For instance, if the array contains tens of thousands of elements, the time required to process all comparisons becomes impractical. The method relies solely on arrays and does not utilize any advanced data structures, making it a direct but inefficient solution. One of the key operations in this approach is the pairwise comparison of elements. For every element at index I, we compare it with each subsequent element to determine whether it is smaller, which is straightforward but computationally expensive. To improve the performance, we can consider optimizations that exploit sorted order or more efficient search methods. For example, techniques like binary search or merge sort trees enable us to reduce the number of comparisons significantly. Edge cases are also important to consider. For an empty input array, the result is simply an empty array. If all elements in the array are identical, every count will be 0 because no element is smaller than another. Similarly, an array with only one element will always have a count of 0 since there are no elements to the right. While the brute force approach offers clarity in implementation, its n squared time complexity makes it unsuitable for very large arrays. To handle such cases efficiently, optimized methods like divide and conquer or segment trees are better suited for this problem. This solution leverages a modified merge sort algorithm to solve the problem efficiently. The key idea is to maintain the original index of each element in the array during the sorting process, which allows us to count the number of smaller elements after each number as we merge sorted subarrays. First, the merge_sort function recursively divides the input array into two halves until each half contains only one element. During the merging step, we compare elements from the left and right subarrays. If an element from the left subarray is greater than an element from the right subarray, it means that all remaining elements in the right subarray are smaller than this element from the left subarray. We then update the count for the left element accordingly. The smaller list is used to store the count of smaller numbers for each element. The enumerate function is used to track the original indices of the elements, which ensures that the counts are recorded in the correct order. The overall time complexity of this approach is n log n, due to the divide and conquer nature of merge sort. This is much more efficient than the naive n squared approach, which involves comparing each element with every other element to its right. This implementation is concise and avoids unnecessary complexity, making it suitable for competitive programming and practical use cases. By using the merge sort technique, we efficiently calculate the required counts while maintaining the original order of the elements. Here, we are implementing the solution to the count of smaller numbers after self problem in Java. We start by importing necessary packages and defining our solution class. Inside it, the main method countSmaller accepts an array of integers, nums. To keep track of both the original indices and values of the elements, we define a helper class called pair. This class has two attributes: index for the element's position in the array and value for its actual value. Next, we initialize an array, smaller, to store the result for each index, and an array, enum_nums, to hold the enumerated pair objects. A simple loop populates enum_nums with the pair objects corresponding to the elements of nums. Finally, we call the mergesort function, which will process the enum-nums array and calculate the counts of smaller elements for each index. Once the merge sort is complete, we convert the smaller array into a list to match the required output format. The code now converts the smaller array into a list integer to prepare the result for return. The mergesort function is the core of this implementation and is defined as a private helper method. It takes the enumerated array enum-nums, the smaller result array, and the current bounds of the segment to be sorted, namely start and end. The function begins by checking if the segment size is 1 or 0, in which case no further sorting is needed. If the segment is larger, we calculate the midpoint and recursively call mergesort for the left and right subarrays. Once both halves are processed, the merge function is called to combine them. This merging step is crucial because it not only sorts the current segment but also updates the smaller array with the count of smaller elements for indices in the left half, based on comparisons made during the merge process. Let's now examine the merging logic in detail. Within the merge function, we use two pointers, left and right, to traverse the left and right halves of the current segment. We also maintain a right count variable to track how many elements from the right half have been merged so far, as these represent the smaller elements relative to the current element in the left half. During the merging process, if the element in the right half is smaller, it's added to the merged list, and right count is increment. Otherwise, the element in the left half is added, and its count of smaller elements is updated by adding right count. After the main loop, any remaining elements in the left or right half are added to the merged list. Finally, the sorted and merged elements are copied back into the enum-nums array to update the original segment. This ensures that the array remains sorted throughout the recursive process, enabling efficient calculation of smaller counts for all elements. To solve the problem, we begin with the input array nums, which is 5, 2, 6, 1. The first step is to enumerate this array by pairing each number with its index, resulting in the array 0, 5, 1, 2, 2, 6, 3, 1. This helps us track the original positions of the numbers throughout the sorting process. We also initialize an array called smaller with zeros, 0, 0, 0, 0, which will eventually store the counts of smaller numbers after each element. The approach relies on a modified merge sort. In the divide step, we recursively split the enumerated array into smaller subarrays until each subarray contains only one element. For this example, we split 0, 5, 1, 2, 2, 6, 3, 1 into 0, 5, 1, 2, and 2, 6, 3, 1, and then further split these subarrays into 0, 5, 1, 2, 2, 6, and 3, 1. These single-element subarrays are now ready to be merged while counting smaller numbers. Next, we begin the merging process. First, we merge the subarrays 0, 5, and 1, 2. While merging, we compare the elements. Since 2 is less than 5, it means there is one smaller number after the number at index 0 in the original array. So, we increment smaller, 0, by 1. The merged result is 1, 2, 0, 5, and smaller becomes 1, 0, 0, 0. Similarly, we merge 2, 6, and 3, 1. Here, 1 is less than 6, so we increment smaller, 2, by 1. The merged result is 3, 1, 2, 6, and smaller is updated to 1, 0, 1, 0. Finally, we merge the two larger subarrays, 1, 2, 0, 5, and 3, 1, 2, 6. During this process, we compare each pair of elements. For instance, 1 is less than 5, so smaller, 0, is increment by 2, accounting for the two smaller numbers. Similarly, 1 is less than 2, so smaller, 1, is increment by 1. After completing all comparisons, the merged result is 3, 1, 1, 2, 0, 5, 2, 6, and smaller becomes 2, 1, 1, 0. With the merging process complete for this example, the final output is the smaller array, which is 2, 1, 1, 0. This means that, for each number in the original array, there are 2, 1, 1, and 0 smaller numbers after them, respectively. Now, let's look at another example. For nums equals 3, 7, 8, 4, we start by enumerating the array to form 0, 3, 1, 7, 2, 8, 3, 4, and initialize smaller as 0, 0, 0, 0. In the divide step, we split the array into 0, 3, 1, 7, and 2, 8, 3, 4, then further split these into single-element subarrays 0, 3, 1, 7, 2, 8, and 3, 4. These single-element arrays are ready for merging. During the merge process, we first combine 0, 3, and 1, 7. Since 3 is less than 7, there are no smaller numbers after 3, so smaller remains unchanged at 0, 0, 0, 0. The merged result is 0, 3, 1, 7. Next, we merge 2, 8, and 3, 4. Here, 4 is less than 8, so we increment smaller, 2, by 1. The merged result is 3, 4, 2, 8, and smaller is updated to 0, 0, 1, 0. Finally, we merge 0, 3, 1, 7, and 3, 4, 2, 8. While merging, we find that 4 is less than 7, so smaller, 1, is increment by 1. Additionally, 4 is greater than 3, so no change is made for smaller, 0. After completing all comparisons, the merged result is 0, 3, 3, 4, 1, 7, 2, 8, and the smaller array becomes 0, 1, 1, 0. In this example, the final output is 0, 1, 1, 0, indicating the count of smaller numbers after each element in the original array. For the third example, where nums equals 1, 1, 1, 1, we begin by enumerating the array as 0, 1, 1, 1, 2, 1, 3, 1, and initializing smaller as 0, 0, 0, 0. During the divide step, we split the array into 0, 1, 1, 1, and 2, 1, 3, 1, and then into single-element subarrays 0, 1, 1, 1, 2, 1, and 3, 1. These subarrays are now ready to be merged while counting smaller numbers. When merging 0, 1, and 1, 1, we find that the values are equal, so no changes are made to the smaller array. The merged result is 0, 1, 1, 1, and smaller remains 0, 0, 0, 0. Similarly, merging 2, 1, and 3, 1 results in no changes since the values are equal. The merged result is 2, 1, 3, 1, and smaller is still 0, 0, 0, 0. Finally, when merging 0, 1, 1, 1, and 2, 1, 3, 1, all pairs of elements are equal, so no changes are made to the smaller array. The final merged result is 0, 1, 1, 1, 2, 1, 3, 1, and the output is 0, 0, 0, 0. This indicates that there are no smaller numbers after any element in the original array. When analyzing the time complexity of this solution, we start with the modified merge sort. Merge sort operates by recursively dividing the array into smaller halves until each subarray contains a single element. For an input array of size n, this division process creates log n levels of recursion. At each level of recursion, the algorithm processes the two halves of the array independently. Next, during the merge step, we compare elements from the two sorted halves and count the number of smaller elements in the right half for each element in the left half. This merging operation involves iterating through all elements in the current level, and since this is done for the entire array, it takes n time at each level. Combining these two factors, the total time complexity becomes n asterisk log n, where log en accounts for the recursive depth of the merge sort, and n accounts for the merging and counting operations at each level. The time complexity of this solution remains n asterisk log n in all cases best, average, and worst, because merge sort always splits and merges the array in the same structured way, regardless of the input order. Turning to space complexity, the main contributors are the recursive stack space and the temporary arrays used for merging. The recursion depth is proportional to the log of the input size, so the stack space is log n. Meanwhile, during merging, we create temporary arrays to hold the left and right subarrays being processed. The size of these arrays is proportional to the size of the current subarray, and while they are reused at each level, the total additional space required remains n. Adding these together, the overall space complexity is n, dominated by the temporary arrays, with an additional log n for the recursion stack. To better understand the efficiency of this approach, let's compare it to a brute force solution. In the brute force method, for each element, you check all subsequent elements to count smaller numbers. This requires n squared time because there are n elements, and each comparison takes n in the worst case. In contrast, the optimized merge sort solution reduces the time complexity to n asterisk log n by using a divide and conquer strategy. It efficiently counts smaller elements during the merge step, leveraging the fact that the subarrays are already sorted. From a mathematical perspective, the merge operation at each level takes O, n, time, and since there are O, log, n, levels of recursion, the total time complexity is O, n asterisk log, n. For space, the temporary arrays used in merging require O, n, and the recursion stack adds O, log, n, resulting in a total space complexity of O, n. In summary, the optimized merge sort solution achieves a time complexity of O, n asterisk log, n, and a space complexity of O, n. These improvements make it significantly more efficient than the brute force approach, which has a time complexity of O, n squared. This difference becomes especially important when dealing with large input sizes, where the brute force method would be far slower and less practical. By leveraging the divide and conquer technique and minimizing redundant comparisons, the merge sort solution offers a scalable and elegant way to solve the problem of counting smaller numbers after self. When working on this problem, there are some common mistakes you should watch out for. First, not accounting for edge cases like empty arrays or single-element arrays is a frequent oversight. Many solutions assume the array has at least two elements, which can lead to runtime errors or incorrect results. To avoid this, explicitly check for these edge cases before jumping into the main logic. Next, using nested loops without considering time complexity is another common issue. A brute force solution with O, n squared, complexity will likely exceed time limits for large inputs, especially when the array size exceeds 10,000. Instead, explore optimized approaches like divide and conquer, binary search, or segment trees. Finally, mistakes in handling indices during recursion or divide and conquer methods can lead to off-by-one errors or even infinite recursion. To prevent this, carefully define and verify your index ranges before making recursive calls or splitting the array. Another common pitfall is failing to use stable sorting when it's required. For problems where the relative order of elements matters, unstable sorting methods can produce incorrect outputs. To address this, use stable sorting algorithms, such as merge sort, which preserve the original order of elements with equal values. Additionally, not pre-processing data for faster queries is a frequent inefficiency. When you repeatedly compute results directly during queries, this can become costly. Instead, you can pre-compute useful information, like prefix sums or Fenwick trees, to make query operations significantly faster and more efficient. For interviews, there are a few key insights to keep in mind. First, pattern recognition is essential. Many problems that involve counting smaller elements or inversions rely on similar techniques, such as merge sort or binary search trees. Being able to quickly recognize these patterns can save you a lot of time during the problem-solving process. Also, make sure to communicate trade-offs. If you start with a brute force approach, explain why it has limitations and why optimization is necessary. This demonstrates your problem-solving skills and your ability to think critically about efficiency. Testing edge cases explicitly is another important habit. Interviewers often evaluate how well your solution handles edge cases, such as arrays with duplicates, sorted inputs, or completely reversed arrays. Finally, know your data structures. Problems that involve frequency counts or order statistics often require specialized data structures like Fenwick trees, segment trees, or balanced binary search trees, so understanding these tools is crucial. This problem is closely related to several others on LeetCode that use similar techniques. For example, LeetCode 493, reverse pairs, also involves counting pairs based on specific conditions and can be solved using merge sort or segment trees. LeetCode 327, count of range sum, employs techniques such as prefix sums and divide and conquer, making it another problem worth studying. Additionally, LeetCode 2426, number of pairs satisfying inequality, requires efficient pair counting and makes use of ordered sets or binary search. By exploring these related problems, you can deepen your understanding of the core techniques and see how they apply to various scenarios. There are also alternative approaches you can consider for solving this problem. Using a binary index tree, or bit, is one option. It's efficient for both queries and updates, with each operation having a time complexity of O, log n. However, the trade-off is that it requires additional space and can be tricky to implement under time constraints. Another common approach is to use merge sort-based counting. This method combines the sorting process with counting to achieve an overall complexity of O, n log n. The downside is that you need a strong understanding of merge sort and must carefully manage indices to avoid errors. Finally, there's the option of using a balanced binary search tree. This provides dynamic insertion in rank queries in log n time, but the implementation can be complex, and you'll need to handle edge cases, like duplicates, with extra care. Each approach has its pros and cons, so choose the one that best fits the problem requirements and your familiarity with the techniques. Great job! You've now learned not only the brute force approach to this problem but also the key considerations for optimizing it. Remember, practice is key to mastering these concepts. Thank you for watching, and I hope to see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!